people who are already online, we can do the usual sound check. Can somebody confirm whether you hear me sufficiently loudly? Okay, it's 1 o'clock local time. Let's get started. And we will do this with the usual technical check. So the video is working. The audio, I did not get any confirmation in the chat yet. Can somebody confirm in the chat whether you hear me and whether you hear me sufficiently loudly? Furthermore, the streaming is definitely on. Let me check the recording button. Yes, that one is on. And audio is confirmed, I see. Okay, so we can give it a go. This is the webinar on the crystallography module, and as usual, before going to the science, let's go to the housekeeping stuff. So the project work, 8 teams have been formed and have started, of which 7 have submitted a work plan. I looked at these work plans, and after this session I will send you the emails with some comments on them, so you can expect these later today. The other announcement is that, as all of us have experienced, the Bilbao crystallographic server, which plays an important role in the crystallography topic, has been down for several days already, which makes it impossible to tackle some of the tasks of the past week. And this is the first time this happens in 10 years or so. So, well, I wasn't expecting this. I also have no immediate alternative, because the Bilbao crystallographic server was chosen for this module because it is one of the very few free places where you can do this kind of crystallographic operations. So at the moment I don't have a free alternative at hand. I found the contact address of the people who maintain the server, so I have contacted them, hoping that, in this way I will get some information on how long it will take. But for the time being, it's down and nothing can be done about it. So we have to cope with that. I still hope that it is a temporary thing and that within a few days the site will be available again. And then hopefully you will find the time to get back to some of these exercises and to to look back at this current feedback webinar, where there are screenshots of the working Bilbao crystallographic server in order to verify for yourself how these tools behave. Good, the crystallography topic. This is a topic where typically people have two opposite opinions. Some people do not like crystallography and find this rather dull, although many of you understand that it is needed. Or, alternative point of view, some people like it, that this is very visual and hands-on, when compared to the more abstract reasonings in the Kohn-Sham and Holmberg-Kohn theorems of the past 2 weeks. So, well, you may find yourself in one of these two categories or somewhere in between. An important aspect of this module was the concept of CIF files, crystallographic information files. And most people after this module know what a CIF file is and why it is used. And many people are aware of places where you can find CIF files. And I listed here again, well, it's a screenshot from the course, a set of several databases where you can find CIF files, either computed or experimentally obtained for crystals, for experimental or computed crystals. And one of the tasks I asked you was, for whatever DFT code you want to use, take a CIF file from a very complicated crystal, deliberately a very complicated crystal with a mineral name Neptunite, and well, take that CIF file and convert it into an input file for your DFT code. And that was, of course, an action that was done in the examples with the silicon crystal, where we had to use the CIF to cell program, where you can now understand what the name means. It starts from a CIF file and it converts this into an unit cell file for whatever DFT code you want to use. And first you specify which CIF file it is, that is the first name here. Then you specify the DFT code that you want to use, in our case often quantum espresso, and then you specify the name of the input file for that DFT code, which is usually a user-defined name. So this you have to do for that Neptunite crystal, where you have now this different CIF file, still for quantum espresso, and you could call this, for instance, neptunite.in. Why is such a thing as a CIF file and the CIF to cell program useful? Well, imagine that we live in a world where there are just 4 DFT codes. There are many more, but let's take this as a thought experiment. And you have done a calculation with one DFT code and you want to repeat that calculation or continue on that calculation in another DFT code. That means you have to transform the input file from one code to another one. And yeah, it's defining a crystallographic unit cell. So this is something fairly unambiguous. So you can write a converter to go, for instance, from VASP input files to quantum espresso input files. And you can do that for every DFT code involved. And in this example, with 4 codes, you will need to write 6 converters. This scales with the number of codes squared. So in a world with some 50 or 100 DFT codes, you would need to write a lot of converters. And that is where the CIF format becomes useful. if every code has a converter from a CIF file to their own input definition, then you just need one converter per code. And also experimental people report their crystallography experiments in CIF format, so you even have a way to translate from experimental info to computational input files. So that is the important role of the CIF format. And this is even more handy if our input files describe very complex crystals, so you don't want to enter every position coordinate of every atom in this unit cell by hand. And CIF file is a very good documentation of this. Now, in this module, we do not care so much about the theory of crystallography. We rather want to do practical crystallography. How can we work with crystallographic tools in order to prepare the correct input for our DFT calculations? And the CIF file is the starting point for that. Here you have the first part of the CIF file of Neptunite. And let's look at this block first. 3 different ways to define or to identify the space group of that crystal. It's space group number 9 with this name in Hall notation and with that other name in Hermann Mauguin notation. If you don't know what these notations mean, that is no problem. Take that just as a label, a name for the space group. That space group is one of the 232 possibilities, and the Bilbao server that you cannot access for now lists all 232 of them. And if we look at number 9, then we find there in yet another shorthand notation, CC, we find there that space group. That can be described in 2 different settings, so there are 2 different lines of it, but that's basically space group number 9. Under the space group name in the CIF file, we see 6 numbers that define the unit cell. Not the atoms in the unit cell, but the shape and the size of the box in which these atoms sit. So we have 3 angles, alpha, beta, gamma, and 3 cell lengths, so the lengths of the 3 edges. And with these 3 lengths and 3 angles, you can construct the red arrows and you have the entire box. The picture here is not specifically for Neptunite, it's a general picture, but the idea is the same. And then we need to know where are the atoms in that box, and that is then listed further down in the CIF file. There you have the coordinates of all the atoms. Plus some symmetry operations, because if you would draw the atoms at all of these coordinates, you would see that you have only part of them. The visual picture that I showed a few slides ago had many more atoms than the ones that are listed in the CIF file, and that is because of the symmetry operations. If you apply these symmetry operations on these coordinates, you will get other atoms that are symmetry equivalent with the one for which the coordinate was given. So per group of symmetry equivalent atoms, only one position is explicitly listed. The other positions are implicitly given via the symmetry operations. So that was for a CIF file. If we translate that to a Quantum Espresso input file, the same information should be there, but it's given in a slightly different way. And here you see how Quantum Espresso defines the size and shape of the unit cell, that box, not with the 6 numbers A, B, C, alpha, beta, gamma, but by the coordinates of 3 vectors, this A, B, and C vector that span the unit cell box. They are given explicitly via their 3 components. So in the cell parameters block, this first line are the 3 components of the A vector, so one of the edges of the unit cell. And this is given in units of this A. So A is here, capital A is here defined as 16.48, and I always forget, is this angstrom or Bohr? For quantum espresso at this place in the file, it's probably angstrom. And so this number multiplied by the relative numbers that are put here, these give the actual size of each of the 3 components. Further down in the CIF file, you have the coordinates of the atomic positions. And Quantum Espresso does not work with symmetry so extensively, so there you will usually find all symmetry equivalent positions. Now, if you try to convert that CIF file for Neptunite as taken from a database with CIF to cell, sometimes, depending on which CIF file you start from, you may get errors, and many people will have run into such warnings. Whereas, I can confirm that if I do this with the same input file on my computer, I get the same warnings, so the warnings are right. However, if you do it with another Neptunite CIF file, so here at the bottom, then there are no warnings. That works well. What is the reason? Well, look at these highlighted atoms. CIF to cell can read labels for chemical elements, but not if they are something different than numbers. So as long as there is lithium 1, titanium 2, silicon 1, oxygen 7, oxygen 8, these are correctly read. But if there is something like silicon A, that will fail, that will trigger that error. So if you have to write a CIF file, or if you run into that error, just delete the labels for the chemical elements and then it will work. You don't have to care about replacing that character label by a number, just delete all labels, it will have no consequences. Other issues you can run into, sometimes you see this warning, site occupancies are not found, assuming all occupancies to be 1. This is a harmless error or harmless warning. It's a warning, it's not an error. And the background reason is that CIF files are also used for experimental crystal characterizations. And some crystals may have one type of positions that is on average occupied by 2 different elements. Say 30% of those sites are occupied by iron, 70% are occupied by silicon. And in an experimental report, this is written as one unique site with 30% iron, 70% silicon. In a unit cell for a DFT calculation, we don't have an atom that is 30% iron and 70% silicon. We have to decide, do we put there a full iron atom or a full silicon atom? So there will always be 100% of the same element on each of the sites for a CIF file that is meant for a DFT calculation. So therefore, in such CIF files, we even don't write what that site occupancy is. And CIF to cell will notice that and will give us a warning, I see no site occupancy, so I assume you always mean 1 or 100%, which is correct. That's exactly what we want. So this warning is not meaningful. You may wonder here, now if I then want to calculate such a crystal that an experiment has such a mixed occupancy, how can I do that? Yeah, there are tricks for that. That is one of the applications of the supercell concept that will be discussed in one of the later modules. And this was a question from one of the previous years that is relevant to think about. Somebody says, now if I have made that conversion and if I look at my quantum espresso input file, it looks like there are 2 formula units of that chemical formula in my unit cell. Is that correct? And that's indeed a relevant question. If you look in the CIF file, the chemical formula that was listed there, if you count the atoms that are in there, we have 40 atoms. And if you then look at your final quantum espresso input file that is stemming from that CIF file, you have 80 atoms. And that is indeed because that unit cell is filled by 2 formula units of that chemical composition. So it's not generally true that if you have a particular chemical formula and you build a crystal that is made by that chemical formula, by that element, it is not generally true that one unit cell contains one of these chemical formula. There can be more of them, in this case 2. Let me look at the chat. There is a question, why are there some minus VE signed coordinates? Where did that happen? Or you mean coordinates with a minus sign? Okay, let me go back to, yeah. So in these input files, sometimes you see indeed coordinates or components of coordinates with a minus sign, and many other positions have no minus sign. That is a matter of convention. In CIF files, and all you need to do is to specify the coordinates of every symmetry equivalent position once, and you can do this symmetrically about the origin, so you can look left and right, up and down, back and forth with respect to the origin, or you can look in the first octant and take only positive coordinates. In a CIF file, both are allowed. In DFT codes, sometimes it is not allowed to use negative coordinates, but then CIF2Cell will translate the negative coordinates from the CIF file to the proper positive coordinates for that DFT code. Okay, the second part of the module elaborates on CIF files, so these space groups, unit cell, Wyckoff positions, concepts that are for some people a bit more confusing. And we also explicitly use the Bilbao crystallographic server, and yeah, of course this year several people reported that on this question, I can use the Bilbao crystallographic server. Yeah, no, it's not available right now. So yeah, I'm aware of that, and of course for the reporting about this, or for making the tasks for this course, there is no penalty involved if you could not do this right now. It was just not possible. Well, we used in the course this task that has many different steps to demonstrate how we can use all the information we can find online to construct input files starting from a single mineral name. And that will involve some steps with the Bilbao crystallographic server. So here I will show you with screenshots what you could have met if the Bilbao server was online, and that I hope you will find the time to look back at once it will be online again. But it remains a useful thought process. So we start from the mineral name litharge. I tell you that's the name of a crystal, and now do different things. For instance, start with Googling for the chemical formula. Which elements are in the litharge mineral and with which relative ratio? And if you Google for this, you find the Wikipedia page of litharge. And if you read the Wikipedia page, you see that litharge is an lead oxide with a 1-to-1 ratio between lead and oxygen. And somewhere it even mentions the space group, so let's just note that for later. So we know it's lead oxide, then search in the COD database what is the crystal that corresponds to that. So find the CIF file. And if you do this in the COD database, you find, for instance, this lead oxide crystal, and you can download here the CIF file. Some people notice, well, if we do that, we find different entries, multiple entries for the same chemical formula. Like here we have lead oxide, the first line, but also lead oxide, the second line. And these numbers are a bit different. These space groups seem to have different names. So what is going on there? Well, in general, there are multiple reasons why you can have multiple lines for the same chemical formula. The most obvious one, it can be that one chemical formula can exist in 2 or more different crystal structures. And then, it's very natural to have 2 different lines. It could also be, especially if you use a database with experimental contributions, that you have 2 different reports for the same crystal, and then 2 different entries. Like in the 1950s, somebody has measured with X-ray diffraction the properties of this crystal, and this is reported in the database. But in 2007, somebody repeated that experiment with much better tools, higher precision, and that's a different entry in that database. So you have to make a judgment which of the multiple entries that are listed there is probably the most accurate one, and so that is the one you will work with. And a third reason, which will be the case for the litharge crystal, that is that there can be different settings reported for the same structure. And if that doesn't tell something to you, we will come back to this in a few minutes. Next step in the process, what is now the space group name of the litharge crystal? And we had read this already in Wikipedia, P4/NMM, and in the COD database, P4/NMM, but with a semicolon 1 added to it. What does that mean? We will come to that. If we look in the space group lists on the Bilbao server, then we can find space group P4/NMM as number 129. And you see there are two entries here, origin choice 1, origin choice 2. These will refer to that extra number that was added. Next step, what are the Wyckoff positions for all the atoms in the unit cell? Again, something that depends on the Bilbao server. We have to go to the WICPOS tool that gives you the Wyckoff positions for all space groups. You have to select space group 129 and then you will get a list of Wyckoff positions. And it is normally recommended to do this in the standard setting, so the button here at the left. What does the other settings mean? Well, there is something like the ITA, the International Tables of Crystallography Volume A, that was long ago a book, a reference book with definitions and conventions about crystallography. And for all space groups, this book lists a series of settings, so places in the unit cell where the origin of your access system can be put and orientations of the axis of that access system. Sometimes, depending on which crystal you use, there are very obvious settings that make your coordinates easier to read, or sometimes for different reasons you want to take different settings. So for all the common cases, the ITA lists for every space group the common choices. And one of them is the standard setting. So if you click this button, you will see your positions in that standard setting. If you click this button, you will see the list of possibilities to choose from. And if you want to define a setting for yourself that is not one of these listed ITA settings, you can take the middle button. But then you really need to know what you are doing. So if I take the standard setting for the Litharge crystal, I get this table. These are all the Wyckoff sites that are consistent with space group 129. And it starts from very symmetrical positions at the bottom, Wyckoff site 2A, to the most general position at the top, Wyckoff site 16K. Now, just with that table, we don't know which are the Wyckoff sites for the lead oxygen crystal. We need to really look at the crystal to get to know that. And that we can do if we have a picture of the unit cell where we can identify the coordinates. For instance, you can go to the COD database, open the crystal, in the entry of that crystal in the database, and then by right-clicking on the picture and select symmetry, and then the fifth item of the list, you will see the filled unit cell with all atomic positions within the unit cell drawn. And by clicking on these, you can get coordinates. Or you can open a similar picture in Vesta that will look like this, here in a way where also the few atoms immediately outside the unit cell are shown, but what matters is only the ones inside the unit cell. And if we look at the lead atoms, so this one here is at coordinates 1/4, 1/4, 0.23, the other one at 3/4, 3/4, 0.77. With this information, I can go back to the Wyckoff table and I see that there is a position 2C that has indeed exactly these coordinates. So the easy numbers, the 1/4, 3/4, they are really there. And that other number, the z coordinate, is a general one. So in our case, z equals 0.23, and then the other one must be the complement to that, either minus z or 1 minus z, and here it's given as minus z, so minus 0.23, but if you take the complement in order to bring it to the first octant, then you have minus 0.23 plus 1, so 0.77, and that is indeed the coordinate there. This z, that is really a free coordinate. So, and what does that mean? It can have any value between 0 and 1, and that will not change the symmetry of that crystal. It will stay in the same space group if you allow that z value to change from 0 to 1. Every crystal that you find in nature will have just one of these z values selected. So for Litharge, the correct z value is 0.23. But if you would find another crystal with other elements in the same space group with the same Wyckoff positions occupied, that in general will have a different z value, maybe z equals 0.29. So it's free in general as far as symmetry is concerned, but for an actual crystal there will always be one unique value. Now, on the forum, in the older posts, you find these messages where people struggle with these two different choices, 1 and 2, that are available either on the Bilbao server or in the COD database. Let's now, here you see how they are in the COD database. You have this 1 and 2. And these correspond to that space group listing origin choice 1, origin choice 2. So let's elaborate a bit on what these mean. Let's take the ITA settings for space group 129, and that will give something like this. And here you see explicitly that space group 129 can have a setting with origin choice 2, and this is the default, or alternatively origin choice 1, where the A, B and C are combinations of the previous A, B and C, the one for the default choice, in this way. You can express this in a matrix. The origin choice 1 is not rotated with respect to origin choice 2, so there is a unit matrix for the rotations, but there is a translation with this translation vector. So all the axes have the same orientations in both in both axis systems, but the origin is translated. And this has an effect on the coordinates, something that has our position 2c, where we found the coordinates of 1 quarter z, in origin choice 2 in the standard setting. Well, that one will have coordinates 1/2 0z in the origin choice 1. And I can demonstrate that with this picture. So the picture here at the bottom left for origin choice 2, that one we have already analyzed. The same crystal with origin choice 1 will look like this, and here our lead atom is at a position 0 on the x-axis, 1/2 on the b-axis, and z in the c direction. Now, what is the reason for using these two origin choices? You will have slightly easier coordinates if you take origin choice 1, there will be zeros in several of the coordinates, and that's always handy. So from that point of view, origin choice 1 looks like a convenient one. However, there is one property that origin choice 2 has that is absent in origin choice 1. And that I want to illustrate by taking that green plane here. Let's cut the crystal along the green plane. It contains these two lead atoms. And let's now extend the plane in all directions and see what do we meet in that plane. And I show here 4 adjacent unit cells, always with that same green cut. And you see that this atom here in the first section, so here, if you mirror this across the origin, so the origin of the axis system was here, and this is the 0, 0, 0 position, well, you will be at a position where there is another lead atom, namely the upper right lead atom of the adjacent unit cell. In other words, there is inversion symmetry across the origin. If you invert all positions across the origin, you will bring an atom to itself. In origin choice 1, this is not the case. If I take this left face here with a lead atom here at the bottom, so here at the bottom, and now I extend this, and this is what happens in that same plane. The origin is here, where there is an oxygen atom, so here is the origin. If I now make an inversion of this lead atom, I come at an empty space. So the inversion operation is not a symmetry operation with that unit cell choice. And for many reasons, especially in calculations, an origin choice with inversion symmetry is much more beneficial. It will, for instance, reduce potentially complex numbers in the calculation to real numbers, which take much less memory in the computer and which are faster to operate on. So if you can do a calculation with an origin choice that has inversion symmetry, your calculation will be much faster than if you do it in the origin choice without inversion symmetry. So which is the reason why the default origin choice is always the one with inversion symmetry. If there is a choice, in some crystals there is no possibility to choose an origin that keeps inversion symmetry. So here you have all of this summarized with the coordinates in the comparison table. Now, if you look at the CIF file for Litharge, you will see one coordinate line for lead. But we have 2 lead atoms in the unit cell. So where is the other one? And that is given by the symmetry operations. So the Litharge crystal has 16 symmetry operations, and if you apply all of them on the lead position, on the lead coordinates, then 8 of them will bring that lead coordinate onto itself, and the other 8 will bring that lead coordinate to the other lead position. So therefore the 2 lead positions are implicitly contained in the symmetry operations. So this was in origin choice 2. If you do the same in origin choice 1, and there you have a different coordinate and your operations may look a bit different, but the effect will be the same. So for the confidence question, I can tell something meaningful about the concepts space group, unit cell, and Wyckoff position if you can follow along what has been discussed in the past few minutes. Then you are sufficiently equipped to apply these crystallographic concepts for DFT purposes. Let me summarize this part in one slide. So we have space group, unit cell, and Wyckoff positions, where space group is a kind of symmetry label. It identifies the main symmetries of that particular crystal, and such a space group, such a symmetry assignment, that partially constrains the types of boxes that are possible. If you have if you have a space group with an hexagonal symmetry, 6-fold rotation axis, you will not find a rectangular unit cell shape there. So only the hexagonal boxes will be consistent with this. There will still be multiple choices of unit cell shapes possible, but some are excluded. So therefore, the space group constrains partially the size of boxes, not the size, the shapes of boxes that are possible. It also constrains partially the Wyckoff positions that are possible within that box. On the other hand, if you take some unit cell with a corresponding set of Wyckoff positions, that fully together, these two together, that fully determines the space group. So it works differently in the two different directions. And what does a CIF file does now? It tells you what the space group of the crystal is, and it tells you what is the unit cell and what are the occupied Wyckoff positions. So together that is a unique definition of the crystal. Sometimes it is or for some people it is a difficult concept what this free parameter in the Wyckoff positions really means, and I have one illustration here to try to help to illustrate that meaning. And the illustration is made for the Litharge crystal. So let's look at this lead position at 1/4 Z, and I consider an axis that is parallel with the Z-axis and that goes through that lead position. That is an axis of 4-fold rotation symmetry. So I can rotate the crystal over 90 degrees about that axis, and then every atom will be converted to a position where the same atom was present. So after the rotation, you will not have noticed that anything has changed. Let's look at it from the top. So now I look along that 4-fold rotation axis. So my green line here, I look on top of that line and I see this line on top, and I've written this as a square to emphasize that it is a 4-fold rotation axis. If you rotate the crystal, well, you see you have around that 4-fold rotation axis this square of lead atoms, and all of them are equivalent to each other because they all correspond to this upper right atom in the unit cell. So if you make a rotation of 90 degrees, then these atoms will be transformed into each other. Same for the oxygen atoms, they also form a square. So yes, really, this is a fourfold rotation axis for this crystal. If I now would change the z, the free parameter z, then half of my lead atoms, so this one in the unit cell, will move up, so this entire square will move up, and the other ones, they will move down, and they too form a square. This is one angle of the square, this is one angle of the square, this is one angle of the square, and here would be another angle of the square. So the inner square will move, say, up, the outer square will move down, but this axis here remains a fourfold rotation axis. So whatever we do with that z-coordinate, the symmetry of the crystal, in this case the example of the fourfold rotation axis, remains unchanged. If, however, we would change other coordinates, if we would move these lead atoms not in the z direction, but in the xy direction, now we are in a position where we still have a square, but it's not centered about that fourfold rotation axis anymore. So if we would apply that fourfold rotation, this position will not be transformed necessarily into a position where the lead atom was. And so this position, if I rotate over 90 degrees, will be here, but there was empty space here before. So this is not a symmetry conserving operation anymore. And that is because you changed a coordinate that was not a free coordinate in the Wyckoff list. Another way to illustrate that, same crystal, other symmetry operation, the inversion about the origin. We have the two lead atoms, one at minus z, one at plus z. If I change z, then one atom will move down, the other will move up, but we still have this inversion symmetry. Or this way, we still have the inversion symmetry. If, on the other hand, I would change one of the z's without changing the corresponding z, so I move just one atom, I do something that is against what the Wyckoff list prescribes, now I have lost my inversion symmetry. So once again, as long as you change coordinates within the freedom that this Wyckoff site gives you, you keep all the symmetry operations. If you go against that, you destroy symmetry operations. Okay, let me look at the chat. No further questions so far. Then in the section on more useful tools, we also looked at building a CIF file from scratch. And there somebody asked, why do we do that? That looks quite elaborate and cumbersome. Why can't we always start from pre-made files? And there are several reasons why you would want to build something from scratch. For instance, if you are studying a crystal, a hypothetical crystal, that never has been before experimentally measured, even not with other elements present. So there is no example, there is no template present. So in that case, you may need to have to build that crystal atom by atom, and only afterwards find the symmetry that is associated with it. Or, and that happens even more often, when you want to build crystals that are not, when you want to build unit cells that are not unit cells for pure crystals, but unit cells to describe a particular defect. Say that you may have reasons to believe that occasionally in your perfect crystal, two atoms swap positions, a point defect where two atoms interchange position, and that this has some impact on the properties of the crystal, well, you will not find a CIF file for that situation in the database. You have to make a supercell, which we will discuss in a further module, and represent the defects in that supercell. So that means you have to build that supercell, the unit cell for that defect crystal from scratch. So that is why it is useful to know how to build such a general unit cell. And that involves adding the symmetry operation, for which we have this findSym tool. Now, the task here was to apply that on that same Litharge crystal. Let's try to build that one from scratch. And if you have tried to do that, then every year there are people who make this very logical mistake. And for instance, I use here origin choice 1. I have my oxygen atom here at the origin, and I start listing the coordinates. I have an oxygen atom at the origin at 0, 0, 0. Then I have one here at the other corner of the unit cell at 1, 0, 0. So I add this one. And then I have one here at the y end, 0, 1, 0. And if you do that and you give that to Stokes findSym, then it will crash and it will tell you, I cannot read that unit cell. Why? Because you have made a unit cell that is completely impossible. This atom here at the corner of the unit cell, well, the atom that is here is not a different one. There are periodic boundary conditions, so this atom and this atom is the same. If you specify this atom at 0, 0, 0, just by the fact that you are using periodic boundary conditions will immediately give you all other atoms at the corners. And does that mean you have 8 atoms now? No, you still have exactly 1 atom, because this atom here at the corner is for 1/8 inside this box, and 7/8 of this atom are inside the 7 other boxes that touch in this point. So 1/8, but 8 times, that is still exactly 1 atom. But you have to, you can specify that single atom by only one coordinate. So you have to put 0, 0, 0, and that's it. By listing all these periodic copies explicitly, you have effectively put 8 atoms on top of each other at the same position. And yeah, that's an illegal CIF file. So keep periodic boundary conditions into account. And for the same reason, the lead atom that is here in the phase center is for 1/2 in this box and for the other half in the neighboring box. And by periodic boundary conditions, it's identical to this atom, which is also for 1/2 in this box. So 2 halves together, that's indeed 1 atom. So you have to specify it only once, either by the coordinates of this one or by the coordinates of this one, but not by the 2 sets of coordinates together. And so this general purpose CIF file, if we look just at, for the lead and the oxygen atoms, in this origin choice 2, your general CIF file would look like this. I take P1 symmetry because I don't want to write these symmetry operations myself by hand. I can read coordinates, but I cannot easily read symmetry operations. So I give the space group number 1 without any symmetry, and I give the explicit coordinates of all atoms in the unit cell, taking periodic boundary conditions into account. And that leads to 2 oxygen atoms and 2 lead atoms. And this one I can now give to FindSim, and it will produce this CIF file out of it, where I have the correct space group 129 with its symmetry operations, and therefore I can, here it will list only 1 coordinate per Wyckoff site. If you want to make another exercise on this, I have here an very simple and simultaneously interesting crystal, yttrium fluor sulfur, YFS. It's hard to imagine, but this is indeed a chemical formula. You see the definition of the axis. The origin is here. The length of the A, B, and C edges is this one. It's rectangular, so all angles are 90 degrees. And the Z coordinates for the atoms where these are not obvious are given. And now you can use this as an example to write a P1 CIF file. It's doable, not too many coordinates to write down, and then to generate the space group out of that and to compare with the information in the database whether this is the correct space group or not. Which completes our discussion of the crystallography week. Once again, a bit hindered by the fact that you couldn't use the Bilbao server in the past week, but for people who watch this video later in the year, well, they will hopefully not have had this problem. Next week we will start 2 weeks on geometry optimization, a very important part also for the project. And so the first half of it will be done in the week that comes. It has, of course, a complement in the Let's Play part. And for the people who watch these feedback webinars live from other time zones, notice that Europe is going into daylight savings time soon. So next weekend, so in UTC, the time of the feedback webinar will be different by 1 hour from next week onwards. That's already keeping track of. It's already listed like that in the overview of feedback webinars. For the people who are within the European time zone, nothing will change. It remains 1 local time, but seen from other time zones, it may be a different moment. So just keep that in mind. With this, we are at the usual weekly exercise. Formulate your 1-paragraph summary for the past module and formulate 1 or more exam questions that you find relevant exam questions about this module and put that in the forum in the next 5 minutes. Also, if you watch this video later, you can do the same exercise. After 5 minutes from now, I will be back to look at the last questions you may have put in the YouTube chat meanwhile. Okay, so thanks for your contributions. And I see one question in the chat. Are we supposed to complete the geometry optimizations for in the coming week? Well, it's not different than for any of the previous weeks, so let me go back to the overview. If you follow the structure as indicated and go to the Let's Play section that is connected to the first half of this module, then you will see the practical tasks that are meant for this week. So follow the logical line, follow the instructions on the website, and that will bring you always step by step at every place where you need to be. Okay, any further question? I wait for a few more seconds. That doesn't seem to be the case, so I will stop here and see you again next week, same time, same place. Bye bye.